Yo, they got me handcuffed. I'm down in central booking. Things are fucked up the way my future's looking. But I'm...
Okay, so here are other formulas for curvature. So here are alternative ones based on what you're given in the problem. Okay, so other formulas for curvature. So basically, this first one here, this is going to be if you have an R of t and it is a regular parameterization. So is regular is a, here I'll go back here. So is a regular parameterization, meaning that it is not an arc length parameterization. So not an arc length parameterization. Okay, ALP, not arc length parameterization. So if you have that, then our curvature formula is a little bit different, and it's a little bit more complicated. But that's just because we aren't. Remember, arc length parameterizations make everything easier, or make calculations easier from there on out. So if we don't have that arc length parameterization, we do have to do a little bit more work. So what our curvature formula is going to look like, it's going to be based on t, not s, because it's not arc length. It's not parameterized by arc length. So anyways, we're going to have the following formula. So we have magnitude of r prime of t crossed with r double prime of t, and all of that, we take the magnitude of all of that on top, and then on the bottom we have the magnitude of r prime of t, and that is to the third power, raised to the third power. Okay, and this is more or less like a plug and chug kind of formula. If you're given an r of t and you want to find the curvature, you just kind of plug it in here. You find the first and second derivatives, take the cross product, find the magnitude, and then you take the magnitude of only the first derivative alone, you cube it and divide whatever you had before by that. It's kind of lengthy, but that's the process you must go through. So anyways, that's the first one. And another formula for curvature is how you can deal with if you're given an x f of x form. Okay, so x and then function of x thing. If that is a point on y equals f of x, so again, if you're given some function of x, right, then your k, and this time with respect to x, k of x, curvature, is going to be the absolute value of f double prime of x. So that's on top, and then this is divided by, in parentheses, 1 plus f prime of x, and this is squared, and then the whole entire quantity on the bottom plus the 1 there is to the 3/2 power. Okay, so this is a little bit complicated. It's more or less just remembering the formula and then applying it to when you have problems like that. Okay, so now I'm going to move on to a couple of other things or concepts that are good to know. They might seem a little bit random, but they are related to what we're doing. So basically, the first one is that t, the unit tangent vector, is going to be perpendicular or orthogonal to the derivative of the unit tangent vector because of the following. T, and we can just write t as the unit vector, dotted with t prime is equal to 0. Okay, and then there's a proof in your book on this, but I won't spend time going over this because it's something useful to know, but you don't need to necessarily know the entire proof behind it every time you use it. Okay, and another thing that's important to know is the following, that our t prime, so the derivative of the tangent vector with respect to t, is equal to dt, dt, right, dt, dt, d capital T dt, there we go, and that is equal to dt ds times ds dt, okay, because then you can just cancel out those ds's, right, and then you get back what we had on the left. And so what that means is that when we take the magnitude of the left side, okay, so if we want the magnitude of d capital T dt, then on the right side what we get is actually the magnitude of dt ds times the magnitude of ds dt, okay? And what this is is actually, so the magnitude of ds dt, that's going to be the derivative of the arc length function, the magnitude of that derivative, right? And that's actually going to be our speed. So that's this, okay? And I just kind of changed the order. I don't know why. But anyway, so that's our speed, right? That's our scalar valued function. And then we're multiplying this times this thing, which we've defined before as our curvature, okay? Remember that was curvature based on, with an arc length parameterization. Okay, so that's an important relation there, and again, I'll write it here. I'll copy it down there. So the magnitude of the derivative of the unit tangent vector with respect to t is equal to this stuff. Okay, so there's an important relation there. Okay, so building off of that, I'm going to introduce the unit normal vector. Okay, so unit normal vector. Alright, so what this is, it's usually denoted with a capital N. We like capitals for emphasis, apparently. So anyways, this is going to be equal to the derivative of the unit tangent vector divided by the magnitude of that derivative of the unit tangent vector. Okay? So this necessarily, you might be asking like, okay, so why are we dividing by the magnitude? Shouldn't it already be a unit vector? No, not necessarily, because we're talking about the derivative of the unit tangent vector. Okay, so this is the derivative of the unit tangent, which might not necessarily be a unit vector itself. So derivative of t, which is the unit vector. Okay, so another way to write this is, let's say we multiply both sides by this magnitude here. So another relation we could get is that t prime of t is equal to our normal vector times the magnitude of t prime of t. Okay, and remember on the last slide, we just found that to be speed times curvature. So another thing we could write here, another way we could rewrite it is n of t times speed times curvature. Okay, so this is a very important one as well. One of the most important ones that you'll learn. So n, another thing to note is just that the normal vector, the unit normal, points in the direction that the curve is turning. That the curve, almost done here, curve is turning. Or bending, whichever way you want to think of it. So basically, like if you have a curve here, and we're analyzing this point, let's say here's our r of t, here's our unit, or just a tangent vector. Okay, we'll just go with the tangent vector, and this will be the normal. Okay, so it points inward to a curve, basically. It's kind of like, I always think of it as like a centripetal force kind of thing. So anyways, that's just a little bit more about the unit normal vector. Okay, so now on to the last topic, and that is of the osculating circle. Osculating circle. So I personally had never heard of this before of like osculating. I've never even heard that word before I took this class. But anyways, it's kind of useful. So I'm just going to tell you the basics about it, and then we'll do an example. I'll do an example in the practice problems video for you guys to see. So what we're doing is, well, I guess you could say an osculating circle is kind of like if you have a curve, then at a certain point, an osculating circle would be more or less like what circle best fits that curve or best hugs that curve at that point, okay? So something like that, and then it would continue on and on and on, like that. So what we're going to have to do is find the center and the radius for this osculating circle. That osculating just means the best fitting circle to the curve. So best fitting circle to the curve at some point. Okay? So again, as I said, I'm just going over the basics here, how to find what we're looking for and what we need. So the radius of curvature, okay, hold on. Let me back up here. Curvature. Try to get all fancy with the letters. Okay, so radius of curvature at, we'll say, point P. Okay, so here's P, point P, is equal to R, We usually just say r for radius. And this is equal to 1 over the curvature at that point. Okay, so whatever you get for, and this is the curvature we've been talking about this entire time. So once you solve for the curvature, you're going to take the reciprocal of it, like 1 over that, whatever number you get, and that's going to be your radius, okay, your radius of curvature. And your center, so the center, okay, I can't write today, I'm sorry. So center of curvature, here we go, center of curvature is going to be found with the following formula. So we have OQ, so this will be our, let's say our origins here, okay, so OQ, this point here, the middle, OQ, that's our center, is going to equal r of t naught plus our radius, the one that we find, the radius of curvature, times the unit normal at that point, okay? And again, the unit normal, I'm just going to refresh your memory, unit normal at a given point is equal to the derivative of the unit tangent vector at that point divided by the magnitude of that derivative of the unit tangent vector. Okay, so that's just a separate thing. That's just a little side note there. So this is the center of curvature down here, okay, at point P. And this is the radius of curvature. So how do we put it all together? Once you get the radius and the center, we're going to combine it in a parameterization for the line, or for the circle, sorry, and for the osculating circle. So our parameterization is going to look like the center, okay? So here's our center of curvature, center, and we're going to add that to the radius of curvature. So here's our radius that we find, and then times the radius, we're just going to stick a cosine t and sine t. All right, so that's basically it. That's what you do with the two pieces of information that we figure out. And as I said, I'm going to show you an example of this in the practice problems video, so you don't have to worry about that. Okay, so that's it for this video. I hope that helped, and happy studying.
But yo, this rap life is real life, sometimes it's full throttle. Right now I gotta think about me, fuck the industry, it gets no love, except those who support me.